Recently in machine learning, counterfactual explanations have received a lot of attention in the domain of basically explaining the results of a machine learning model. The objective is to create post hoc explanations as to why a certain inference has been made, which in the domain of graphs often led to things such as removing existing edge or other transformations such as adding a non-existing edge to the graph. This work again focuses on graphs and counterfactual explanations, and rather than these simple changes such as removing or adding edges, focuses on more advanced approaches of density-based counterfactual framework. The two main methodologies that they have is opening and closing the triangles in the structure of the graph and focusing on the maximal cliques. They empirically validate this framework and show that using this kind of density-based counterfactuals focusing on structures is important in interpreting the basically learning of a model from a graph. As for the notations, you have graph G, you have set of vertices, set of edges. A subgraph is an edge of basically vertices and edges associated with the subgraph, and a subgraph edge is a k-clique if the edge is k, and if it has all the edges. The density of a subgraph is defined as the number of edges like this. They consider the task of binary graph classification mapping a G to 0 and 1 and work with this. When you have a graph G, they define a counterfactual graph as G prime, which basically is still a graph, and is a graph in which the prediction that a model makes on it is the inverse of the prediction that it makes on the actual original graph. So G is the graph, G prime is the counterfactual. In short, in the domain of counterfactuals, the goal is to understand or to find out what to change in the observation in order to flip the output. However, you should not stray away too much, so the desired properties are similarity to the original. There's the sparsity, meaning that the change only affects a few features in order to reduce the combination of effects of changing multiple features. Efficiency, which means that basically generation of the counterfactuals should be fast, and feasibility. So 4 to be exact. If you have a graph G and G prime, they define this distance between them as the symmetric difference between their edges. So this is the set of edges in G that are not in G prime, and this is the set of edges in G prime that are not in G, and you have the summation of the cardinality of these two subsets as being the distance between G and G prime. In section 4, they start talking about the density-based counterfactual search, or in short, DCS. In short, they have this step that they do iteratively, meaning that you go from G to G prime. So initialize G prime as G, and while the output is still the same, you do this transformation. You basically find a sparse region in G prime and densify it, and a sparsified dense region in G prime, and you continue this alteration approach so as to get a G prime in which the output is not the same as G. They have a triangle-based approach as well, meaning that you take the sorted list of candidate edges to remove and to add in order to kind of remove and add new triangles. And you can see that this kind of removal and adding is performed so as to again flip the output with this counterfactual. To score the edges, they focus on the number of triangles that include a certain node, for example. So, for example, if you go over the possible edge between V and U, you basically get the number of triangles that V is a part of, number of triangles that U is a part of, and then go over this. So V and U, if there is currently an edge, then you're going to want to know if this is going to be a candidate for the removal of such edge. And if it doesn't exist, you want to add it to the possible edges to be added in order to create, let's say, a new triangle. So the score would be the summation of these two, or the sum of their influence in some sense. And they would sort it in ascending order, meaning that the smallest are being prioritized for E- for the edges that are candidate for removal, and the other way around for E+. This also shows their algorithm for the clique-based version, in which the key components are this sparsification and this densifications. The paper brings in and discusses these densify and sparsify algorithms as well. The metrics that they have considered are flip rate, or the percentage of graphs in the dataset for which the algorithm was able to find counterfactual explanations. There is the edit distance, which is that difference between them, divided by the cardinality of the union of their edges. And the calls, meaning the runtime complexity in terms of the number of calls to the black box model. This figure has some examples of the counterfactual graphs that the algorithm has found. You can see that the methodology works great compared to, let's say, the edge-based approach. And note that this data here is basically going through the dataset and finding an example, which actually is an example with the flipped class. Therefore, by definition, it would have 100. On the left, you will see the symmetric differences between the original and the counterfactual examples. You could see that the data-based approach is basically the highest in most cases, and the edge and the triangle filling and unfilling part, which is also kind of similar to the edge, are the lowest. But you can see that there is a reasonable distance between the counterfactuals and originals in these approaches based on cliques. In terms of the number of calls to the oracle, also you can see that this data is the highest ones. And at the same time, you could see that in terms of this kind of computational efficiency, the clique-based approaches and the triangle-based approaches, or the approaches proposed in this paper, are working reasonably good.